And so that's what these instruments are doing. They're looking for polarization, not of optical light, but of microwave light from the Big Bang, the leftover heat from the Big Bang. So remember I said inflation. Inflation is this theory that there's this quantum field that fluctuated, that produced everything that we know and love about the Big Bang. It would also produce what are called gravitational waves, waves in the fabric of space-time itself. Those waves perturb the electrons, the protons, the early hydrogen atoms in the universe when the CMB, or cosmic microwave background, was produced about 400,000 years after the Big Bang. When light interacts with matter, as you see from the glare, it becomes polarized. That matter would be polarized. That matter in its orientation would change depending on how much gravitational wave energy was present when the CMB was produced. So it's actually a gravitational wave detector. We're using the photons of the cosmic background as a type of film, if you will, and onto which these waves of gravity, if they exist, and only if they exist,
they get
they get a polarization to them, a curling, twisting pattern of polarization we call it B-mode polarization.
Wow.
So it's a lot of logical steps, but actually it's very well tested and very well theorized. It just hasn't been detected yet.
It's quality physics going into that. Yeah.
That's super cool, man.
Yeah. Yeah, literally. And we can't use an iPhone. We got to cool our detectors down to my colleague Suzanne Staggs at Princeton. She's built detectors that operate at 0.1 degree above absolute zero.
Right.
Using isotopes of helium. She does incredible stuff. And they're superconducting detectors. They're basically little thermometers. So, you go outside, and not in New York, but in San Diego, you go outside, you can see the sun with your hand. You can basically detect where the sun is using its infrared and that your skin can absorb infrared heat. Well, so too, we can have detectors that can see microwaves and infrared radiation, but they have to operate where it's really cold. Otherwise, It's like building, the biggest, James Webb Space Telescope and putting it in Manhattan.
And so what's the fluctuation of temperature that you're looking for between what the universe has cooled to and what would have been present right at the Big Bang?
Yeah, exactly what we're looking for. So there'll be deviations in about a part in a billion, so a nanokelvin. So in other words, if the universe on average is about 2.7 Kelvin, it would be 2.7 plus a nanokelvin in that direction, and 2.7 minus 1 nanokelvin. So you're looking at the 9th decimal place, right? So
a billionth of a degree.
Above absolute from.
Wait. And somebody gave you money to do this?